Somewhere in the dark between galaxies, a massive star is nearing its last quiet hour. From the outside, it still shines with the calm blue light of something ancient and steady. Deep inside, where no telescope can look, its center has become heavy with iron, and the old balance that held it open against gravity is beginning to loosen. Before this slow path through the death of a star begins, take a moment to settle in. If this kind of deep space storytelling brings some calm to the end of the day, a like, a subscribe, or sharing the video helps this channel continue growing in the quiet corners of the internet where people come to rest and listen. And if it feels right, leave a comment with where in the world this is playing and what time it is there. Maybe it is after midnight beside a small lamp. Maybe it is early morning with the curtains still closed. Maybe the room is dark, the fan is turning softly, and the sound is low enough to become part of the background. Let the screen dim if it needs to. Let the shoulders drop a little. The story ahead is not meant to rush. It moves at the pace of starlight crossing empty space, through layers of burning gas, collapsed cores, ghostly neutrinos, and the quiet ashes that later become worlds. The star at the center of this story is not dying all at once. It has been preparing for this ending since the moment it first began to shine. Its light is still reaching outward, but far below the surface, gravity is waiting. A star looks peaceful only from far away. Seen from the dark between worlds, it is a small point of light, steady enough to guide ships and mark seasons. Its surface gives no sign of the work below. Light leaves it in every direction, crossing empty space in thin golden streams, while the body of the star remains round, bright, and whole. Inside, nothing is still. A star is held open by the same force that is always trying to close it. Gravity pulls every layer inward. It is present everywhere in the star, in the outer gas where atoms drift through pale heat, in the deeper layers where the pressure grows heavy, and in the core where the weight of everything above presses down without pause. Every particle feels the pull toward the center. Every layer rests on the layers beneath it. The whole star is carrying its own mass. If gravity acted alone, the star would not remain wide and luminous. The gas would sink inward. The entire object would fall inward until some other force stopped it. But gravity is not alone in a living star. In the core, where pressure and temperature become high enough for atomic nuclei to move with great speed, fusion begins. Hydrogen nuclei collide and join, forming helium, and a small part of their mass becomes energy. That energy does not simply appear as light at the surface. It begins deep inside, as heat, radiation, motion, and pressure. The pressure pushes outward. Gravity pulls inward. Between them, a star finds its shape. This balance has a quiet name in physics: hydrostatic equilibrium. It means that, layer by layer, the inward weight of the star is matched by outward pressure from the hot material inside it. The word sounds dry, but the thing itself is delicate. A sphere of plasma wider than planets, heavier than imagination easily holds, can remain stable because each depth supports the depth above it. The lower layers push up, the upper layers press down. The star neither falls into itself nor flies apart. It breathes without breathing. The light that reaches the surface began in the core a long time earlier. A photon born near the center does not fly straight outward like a beam from a lamp. The interior is too dense for that. It scatters from particle to particle, absorbed and re-emitted again and again, losing direction, changing energy, wandering through a maze of hot matter. The journey can take thousands of years before that energy finally reaches the outer layers and escapes into space as starlight. By the time light leaves the star, the process that made it may belong to a much earlier chapter of the star's life. This is why a star can seem simple from the outside and yet be filled with history inside. The surface is only the last page of a long passage of energy. Below it, temperatures rise inward, density rises inward, and matter becomes less like anything familiar on Earth. Electrons no longer remain bound to individual atoms. The gas becomes plasma, a sea of charged particles moving through radiation and magnetic fields. There is no flame in the ordinary sense. There is no burning wood, no smoke, no oxygen feeding a fire. A star is not on fire. It is a place where atomic nuclei are being pressed close enough for the strong nuclear force to bind them together. That difference matters. Fire is chemistry. A star is nuclear. In a star like the Sun, the main fuel is hydrogen. The core is hot enough for hydrogen nuclei, single protons, to overcome part of their electrical repulsion and fuse through a chain of reactions into helium. The process is slow for any individual particle. It must be slow. If the Sun's core converted all its hydrogen quickly, the Sun would not shine for billions of years. It would flare and fade. Instead, the reactions occur at a measured rate, restrained by the very conditions that make them possible. The star spends its fuel with great patience. For most of its life, this patience is enough. The outward pressure from fusion balances the inward pull from gravity, and the star remains on what astronomers call the main sequence. That phrase does not describe a place in space. It describes a long, stable phase of stellar life. During this phase, the star is mostly doing one thing in its core, turning hydrogen into helium. The surface may flicker with magnetic storms. The outer atmosphere may throw charged particles into space. But deep below, the main work continues, steady and hidden. The balance is not frozen. It adjusts constantly. If the core contracts slightly, the temperature rises, fusion becomes more active, and the increased pressure pushes the core outward again. If the core expands slightly, the temperature drops, fusion slows, and gravity pulls it back. In this way, a star behaves like a system with a built-in correction, always leaning one way and then the other, never perfectly motionless, never fully unstable. It is not a statue. It is a negotiation. The larger the star, the heavier that negotiation becomes. More mass means stronger gravity, and stronger gravity means the core must become hotter and denser to push back. A small red dwarf can live gently for a length of time far beyond the current age of the universe, burning its hydrogen so slowly that its future is almost unimaginably long. A star like the Sun burns faster, but still with enough restraint to last around 10 billion years. A much more massive star must push far harder against itself. Its core runs hotter, its fusion rate climbs, its surface shines with a brightness that can make the Sun seem modest by comparison. Brightness has a cost. A massive star does not live longer because it has more fuel. It lives shorter because it spends that fuel at a much greater rate. Its light is not thrift. It is expenditure. Every moment of brilliance is paid for by reactions deep in the core, where hydrogen is being consumed faster than in smaller stars. Such a star may contain many times the Sun's mass, and yet live only millions of years. In a galaxy where some stars endure for tens or hundreds of billions of years, a few million years is brief. It is a flame held high and fed too quickly. From outside, the massive star can appear serene. It may shine blue-white, with a surface hotter than the Sun's, pouring ultraviolet radiation into nearby space. Its winds may stream outward, lifting material from its surface and sending it into the surrounding darkness. Nearby gas clouds may glow under its light. Dust may be pushed aside. New stars may begin forming in the carved spaces around it. A massive star changes its neighborhood simply by existing. Yet the most important changes are not outside. They are buried in the core, where the star is slowly altering its own future. Hydrogen becomes helium. Helium collects as ash from the first long stage of burning. The core that once had fresh fuel becomes richer in the product of its own work. The star does not notice this as a sudden event. There is no single instant when everything changes. The shift is gradual, like a lamp whose oil level is falling in a room where the light still looks steady. The condition of the star depends on something simple and unforgiving. The core must keep producing enough pressure to resist gravity. As long as fusion supplies that pressure, the star can hold its form. If fusion weakens, the balance changes. Gravity does not need to become stronger. It only needs the resistance to become weaker. That is one of the quiet truths of stellar death. Gravity has been there from the beginning, patient and exact. It does not arrive at the end. It waits. For now, in this first stage, the star is alive. The core is hot. Hydrogen still fuses. Energy still moves outward through dense layers and finally escapes into space. The surface still shines with the calm appearance of stability. Around it, planets, dust, or empty orbits would receive its light without knowing how carefully that light is being maintained. But inside every massive star, the balance has a direction. Hydrogen will not last forever. Helium will gather. The core will change. What seems steady from the outside is already moving, very slowly, toward the next layer of its life. The star holds itself open tonight, as it has for ages, with gravity below every layer and fusion burning at the center. For a while, that is enough. A massive star spends its life in a hurry that cannot be seen from its surface. It may appear calm, blue, and clean against the black around it. But the calm is only the outer face of a faster clock. Deep inside, its core is burning through fuel at a rate that smaller stars never approach. The star has more matter than the sun, sometimes many times more. Yet that greater store does not grant it a longer life. It gives gravity more weight, and gravity demands a hotter answer. The answer is fusion pressed into a higher gear. A low-mass star can be economical with its hydrogen, holding a small, steady fire in its center for lengths of time beyond the age of the universe so far. A star like the Sun is less patient but still long-lived, spending billions of years in a quiet main sequence balance. A massive star does not have that luxury. Its own weight squeezes its core until the temperature climbs, and the hotter the core becomes, the faster the nuclear reactions run. The star shines brighter because it is spending itself faster. This is one of the first reversals in the life of giant stars. More fuel does not mean more time. In ordinary life, a larger store of fuel might suggest a longer flame. In a massive star, the opposite is true. The extra mass presses down so strongly that the core must burn with far greater intensity to keep the star from collapsing. A star with many times the mass of the Sun may pour out tens of thousands of times more light. Its surface can flood nearby gas clouds with ultraviolet radiation. Its winds can scrape material from its own outer layers and cast that material into space. It looks powerful because it is powerful, but the price is time. A star roughly 20 times the mass of the Sun may live only around 10 million years before leaving the main sequence. 10 million years is long beside a human life. It is long beside mountains, rivers, forests, and species. But for a star, it is short. The Sun will spend around 10 billion years in its central hydrogen-burning phase. The giant star spends perhaps 1,000th of that. It appears, lights its surroundings, reshapes the gas around it, and begins moving toward death, while smaller stars born in the same cloud are still near the beginning of their lives. In a young stellar nursery, this difference becomes almost visible. A cold cloud of gas collapses into many stars at once. Some are small red dwarfs, faint and quiet. Some are sun-like, yellow or white, settling into stable lives measured in billions of years. A few are massive, blue, and bright enough to carve cavities in the cloud that formed them. These giants dominate the scene. Their light ionizes hydrogen gas, making it glow in soft red sheets. Their winds push dust into arcs and walls. Yet those most brilliant stars are also the first to leave. They do not travel through a slow old age like the sun will. They move through their stages with increasing speed, because every change in the core demands a hotter and more urgent form of fusion. When hydrogen is abundant in the center, the star can hold itself for millions of years. Hydrogen nuclei are light. The reactions are efficient enough to provide pressure for a long time. The star's core turns hydrogen into helium, and helium slowly gathers like ash in a place where the fire has not yet gone out. After a long while, the central hydrogen thins. Fusion in the core weakens. The outward pressure softens slightly, and gravity answers at once. The core contracts. As it contracts, it heats. Around the helium-rich center, hydrogen still remains in a shell, and that shell begins to burn. The outer layers respond by swelling and changing. The star may become a supergiant, larger and cooler at the surface, or remain blue and hot depending on its mass, rotation, chemical makeup, and how much material it loses through winds. There is no single face that all dying massive stars wear. The deeper story is written by the core. Once the helium center becomes hot enough, helium fusion begins. 3 helium nuclei can combine to form carbon through the triple alpha process, and some carbon can capture another helium nucleus to become oxygen. These names are familiar because they belong to ordinary life, but their birthplace is not ordinary. Carbon and oxygen are made in the compressed centers of stars, where matter is stripped into nuclei, and electrons, where heat is not flame but motion, where pressure is not a hand pushing outward, but the collective insistence of particles that cannot be squeezed without response. For a massive star, helium burning lasts far less time than hydrogen burning. The clock has changed. The first stage lasted millions of years. This next one may last around 1 million years, or less, depending on the star. The star is still bright. It may still appear steady, but its inner life is now passing through chapters more quickly. Each fuel that follows will require a higher temperature to ignite, because heavier nuclei carry stronger positive charges and resist being pushed together. Gravity must contract the core more tightly. The core must heat further. Fusion must become more demanding. The star is not simply using fuel, it is climbing a ladder made of pressure. When helium in the center is spent, the carbon and oxygen core contracts. Hydrogen and helium may still burn in shells above it, layers of activity stacked around a deeper silence. The contraction raises the temperature again, until carbon itself can fuse. Carbon burning creates elements such as neon, sodium, and magnesium. It does not last long. In a massive star, this stage may endure for only centuries or thousands of years. That is still long enough for civilizations to rise and vanish on a planet far away. But inside the star, it is a late hour. After carbon comes neon. Neon burning requires still higher heat, and it can involve high-energy light-breaking neon nuclei apart before the fragments are captured into heavier elements. This stage may last only years. The star may look almost unchanged during those years. Light from its surface keeps leaving. Winds keep flowing. If worlds orbit nearby, their skies may show the same bright star night after night. But the core is no longer living by the long rhythms of youth. Then oxygen burns. The core becomes hotter again, denser again, closer to the end. Oxygen fusion can build silicon, sulfur, and related elements. This stage may last months, perhaps less than a year in some massive stars. The pace is now strange. The star once measured its life in millions of years. It is now spending entire nuclear chapters within the span of seasons. Finally, silicon burns. This last major fuel does not burn in the simple way hydrogen does. At temperatures of several billion degrees, high-energy photons break nuclei apart and rebuild them through a chain of captures and rearrangements. The products move toward the iron group. Silicon becomes sulfur, argon, calcium, titanium, chromium, nickel, and iron through a complex flow of reactions. The process may last only days, sometimes less. The core now changes faster than the outer body can show. This gives massive stars a strange silence at the end. From the outside, there may be no obvious warning. The same light shines outward. The same surface glows. The last burning stages happen deep inside, hidden beneath layers so thick that the surface cannot immediately reveal what the center is doing. The heart of the star is racing while the face remains calm. The short life of a giant star is therefore not short because it lacks material. It is short because its own greatness forces it to live at higher pressure and higher heat. Every extra layer adds weight. Every added weight demands more fusion. Every stronger fusion spends the fuel faster. The star's brilliance is not separate from its fate. It is the very path toward that fate. By the time silicon begins to leave iron behind, the star has already passed through most of its possible answers to gravity. It has changed hydrogen into helium, helium into carbon and oxygen, carbon into heavier ashes, then onward through neon, oxygen, and silicon. Each stage has kept the star open a little longer. Each has bought time. Less time than before, the giant still shines. Its light still moves out into space. But in the center, the long clock has become a short one. The inner life of a massive star becomes layered because the core cannot remain the same core forever. Each fuel leaves behind an ash, and each ash, under enough pressure, can become the next fuel. The star does not burn through these stages like a candle shrinking from the top. It builds inward, then outward, then inward again, until its center becomes surrounded by shells of different fires, each one belonging to a different moment in the star's past. Hydrogen begins the long story. In the young, massive star, the central region is rich with hydrogen nuclei, moving through a sea of plasma. The temperature is high enough for fusion to occur, and the pressure is strong enough to keep the star from falling into itself. Hydrogen changes into helium, and the energy released by that change moves outward through the star in slow, wandering paths. For millions of years, this is the main work. The core makes helium. The star shines. Gravity waits beneath every layer. As helium accumulates in the center, the star becomes different from the inside out. The hydrogen fuel in the central region thins, and the direct support from hydrogen fusion begins to weaken there. Gravity presses the helium-rich core tighter. The core contracts, and contraction brings heat. Around the core, where hydrogen still remains, a shell of hydrogen fusion can continue, wrapped around the helium center like a bright ring hidden inside the star. The star now has more than one active region. It is no longer a simple hydrogen-burning center. It has begun to separate into layers. When the helium core becomes hot enough, helium itself can fuse. This requires a much higher temperature than hydrogen fusion, because helium nuclei carry more positive charge and resist being pushed together. In the deep center of the star, 3 helium nuclei can combine through the triple alpha process to form carbon. Some of that carbon captures another helium nucleus and becomes oxygen. In this way, the star begins making elements that feel close to ordinary life, though their birthplace is anything but ordinary. Carbon, later found in cells and wood and breath, begins as a product of pressure and heat in a stellar core. Oxygen, later bound into water and rock and living tissue, forms in the same hidden furnace. The word furnace is only an image. There is no solid wall around this place. There is no flame licking upward. There is only plasma, gravity, radiation, and nuclei colliding in conditions that make familiar matter impossible. The core is not burning in air. It is changing the identities of atoms. Helium burning does not last as long as hydrogen burning. It cannot. The star must work harder to hold itself up, and each later stage gives less time than the one before. When helium in the center is used up, the core is no longer mostly helium. It has become rich in carbon and oxygen, the ash of the helium-burning stage. Hydrogen may still burn in an outer shell. Helium may still burn in a shell below that, but the center itself has again gone quiet, at least for a while. Gravity notices the silence. The core contracts again. The contraction raises the temperature until carbon can ignite. Carbon nuclei are heavier and more strongly charged than helium nuclei, so they require still harsher conditions before they can fuse. When carbon burning begins, the star enters a stage that feels late, even if the surface still looks steady. Carbon fusion produces elements such as neon, sodium, and magnesium. The reactions are more complex than the earlier hydrogen stage, and the time available is shorter. The star is now changing its center on timescales that no longer resemble its youth. A process that once took millions of years has given way to stages that may last only thousands of years. Around the carbon-burning core, the older shells remain. Hydrogen fusion may continue farther out. Helium fusion may continue deeper in. A layer of carbon burning now sits below them. Each shell is separated by temperature and composition, not by a hard boundary. The star is fluid, gaseous, and luminous, but its interior has structure. It is a layered body of heat, each zone shaped by what the zone above and below has already become. After carbon is depleted in the center, the same pattern repeats. The core contracts. It heats. Neon becomes the next fuel, though neon burning has a strange beginning. At very high temperatures, energetic light can strike neon nuclei and break them apart. The fragments then take part in reactions that build heavier nuclei, including oxygen and magnesium. This is not a calm flame advancing through material. It is a storm of particles and radiation, happening deep enough that the surface gives almost no sign of it. Neon burning may last only years in a massive star. The word years feels human, tied to seasons and calendars. But in a star that once lived by millions of years, it is a final shortening of the breath. While this stage unfolds, the outer layers can still shine with apparent confidence. Light still leaves the surface. The star may still be catalogued as a supergiant, a point or disk in a telescope, a bright object with spectral lines and color and temperature. Its core, however, is moving quickly now. When neon is exhausted, oxygen burning follows. The core contracts again, reaching a higher temperature. Oxygen nuclei begin to fuse, building elements such as silicon, sulfur, phosphorus, and related nuclei. This stage can pass in months. A star that has existed since before any human history could now alter its deepest composition during less than a single orbit of Earth around the Sun. The contrast is quiet, but immense. The outer body is vast. The inner clock is small. The layering becomes more pronounced. Outside lies hydrogen, the oldest and lightest material, much of it never hot enough to fuse. Below it, helium remains from the first great transformation. Deeper still are regions enriched in carbon and oxygen. Below those are neon, magnesium, oxygen, silicon, and sulfur, depending on how far the star has evolved. At the center, after the final stages advance, Iron group elements begin to gather. The star resembles an onion only in the sense of nested shells. It is not cold, not solid, not neatly divided. It is a living gradient of pressure, heat, and nuclear history. The last major burning stage is silicon. By the time silicon ignites, the core is under severe compression and the temperature has climbed to several billion degrees. Silicon burning is not one simple fusion reaction. High-energy photons break nuclei apart, and the fragments are captured into heavier nuclei through a chain of rearrangements. Sulfur, argon, calcium, titanium, chromium, nickel, and iron group material appear as the nuclear flow moves toward its final resting place. The center of the star is now building the one kind of ash that cannot become a useful fuel for ordinary stellar fusion. Silicon burning may last only days. In some massive stars, it may be even shorter. The star has spent millions of years in one stage, then far less in the next, then less again, until the final burning happens, almost like a secret held beneath the surface. There may be no visible alarm. There may be no sudden dimming, no bright warning, no sign that the interior has entered its last work. The light coming from the surface is still the delayed result of energy that took time to move outward. The surface is not a window into the present core. It is more like a memory arriving late. By now, the massive star is a set of clocks running at different speeds. The outer layers move slowly. The surface light changes slowly. The winds carry material into space at their own pace, but the center moves from fuel to fuel with growing urgency. Each stage leaves the next one behind. Hydrogen leaves helium. Helium leaves carbon and oxygen. Carbon leaves neon and magnesium. Neon and oxygen help build silicon and sulfur. Silicon builds the iron group core. This is how the star prepares for its ending without yet exploding. It makes the conditions of its own collapse. It does not do so with intention, only with physics. Gravity compresses, fusion answers, ash gathers, and then the ash becomes fuel if the temperature rises high enough. But this sequence has a limit. It cannot continue forever up the periodic table. The deeper the star goes, the less generous the reactions become. The energy margin narrows, the time shortens, the center grows heavier. At the end of this layered burning, the massive star is no longer one simple sphere of hydrogen and light. It is a record of everything it has done to survive. Each shell is a former answer to gravity. Each layer is the remains of a fuel that once held the star open. The outer surface still shines into space, soft and distant. Beneath it lie rings of helium, carbon, oxygen, neon, silicon, and sulfur, all surrounding the quiet accumulation at the center. Iron is gathering there now, and iron changes the story. Iron enters the center of a massive star quietly. It does not arrive as a spark or a flare. It gathers as ash, built by the last fever of silicon burning, nucleus after nucleus, until the deepest part of the star becomes a compact weight of iron group matter. Around it, shells still burn. Hydrogen may still glow in the outer regions. Helium, carbon, oxygen, neon, and silicon may still take part in their own reactions above the center. But the core itself has reached a different kind of material. For most of the star's life, every new fuel has offered another answer to gravity. Hydrogen answered first, giving the star millions of years. Helium answered later, making carbon and oxygen. Carbon, neon, oxygen, and silicon each answered in turn, though each one spoke for a shorter time. The pattern seemed almost reliable. When one fuel was exhausted, the core contracted, heated, and found another fuel deeper in the periodic table. Gravity pressed. Fusion responded. The star stayed open. Iron breaks that pattern. The reason lies in the way atomic nuclei hold themselves together. Every nucleus is made of protons and neutrons bound by the strong nuclear force. Some nuclei are loosely bound, and some are more tightly bound. When light nuclei fuse into heavier nuclei, up to the iron group, the final nucleus is usually more tightly bound than the pieces that made it. The extra binding appears as released energy. That energy warms the stellar core, raises pressure, and helps resist the inward pull of gravity. This is the bargain that keeps a star alive. Iron does not offer the same bargain. Iron group nuclei sit near the most tightly bound state that ordinary stellar fusion can reach. Trying to fuse iron into heavier nuclei does not release useful energy. It takes energy away. The star can no longer turn inward pressure into outward support by moving beyond iron. The old path ends at the very place where the core has become heaviest. Iron is not dangerous because it burns. It is dangerous because it does not. At the center of the star, the iron core becomes a kind of cold fact inside unbearable heat. The word cold does not mean low temperature. The core is hotter than any ordinary matter can be imagined to survive. It means cold in a deeper sense. Iron cannot give the star a new source of pressure through fusion. It cannot become the next bright answer. It sits there, dense and growing, while silicon burning in the shell above continues adding more iron group material onto it. This is how the end approaches without a visible flash. The iron core grows by accumulation. Layer by layer, ash from the surrounding burning shell settles into the center, increasing the mass that must be supported. The core is roughly the size of a planet in this late phase, but it contains a mass moving toward the limit that quantum matter can bear. The outer star is huge, but the fate of the whole object is now being decided in a hidden region much smaller than the star around it. There is still pressure in the iron core, but it is no longer the familiar pressure of fusion pushing outward. Much of the support comes from electron degeneracy pressure, a rule of quantum physics expressed in matter that has been crushed far beyond ordinary density. Electrons resist being packed into the same state. They do this not because they choose, and not because they are hot, but because the Pauli exclusion principle forbids identical electrons from occupying the same quantum state in the same place. As density rises, electrons are forced into higher and higher energy states, and their resistance creates pressure. This pressure is strange because it does not depend mainly on heat. A normal gas pushes harder when it gets hotter. A degenerate core can push back even as it loses thermal energy. The star's iron core holds itself up with quantum mechanics rather than with a living nuclear fire. But this support has a limit. Subramanian Chandrasekhar showed that electron degeneracy pressure cannot hold up a stellar core beyond a certain mass, roughly 1.4 times the mass of the Sun, for a cold white dwarf-like object. There is only so much weight that electron degeneracy can carry. Once the core becomes too massive, the pressure cannot increase fast enough to balance gravity. The iron core is being pushed toward that threshold while the rest of the star continues around it. Shells burn. Energy moves outward. The surface may still shine with no clear sign of the approaching failure. The core, however, is growing heavier, hotter, and more tightly packed. The electrons are being squeezed harder. The nuclei are pressed closer together. The margin between support and collapse becomes thin. Then the core begins losing support from more than one direction. At very high temperatures, photons in the core carry enough energy to damage the iron group nuclei themselves. These are not ordinary photons of visible light. They are gamma rays, packets of energy born in a furnace of billions of degrees. When they strike iron nuclei, they can break them apart. This process is called photodisintegration. Breaking a tightly bound nucleus requires energy, and that energy is taken from the core. The star has already reached the fuel that cannot pay it back. Now even the iron ash begins consuming the energy around it as it is torn apart. Heat that helped provide pressure is spent undoing nuclei. The core loses strength at the exact moment when it needs strength most. It is as though the floor beneath the center has begun to drink the weight placed on it, becoming weaker with every added load. At the same time, electrons begin disappearing into protons. Under the rising density, an electron can combine with a proton to form a neutron and a neutrino. This is electron capture. The new neutrino usually slips away, carrying energy from the core. The neutron remains. The electron is gone. With each captured electron, a tiny part of the electron degeneracy pressure is removed. The process does not need to remove every electron. It only needs to remove enough. The core is already close to the edge. Photodisintegration drains thermal support. Electron capture reduces quantum support. Neutrinos carry energy outward into the surrounding star and beyond. Gravity has not changed its nature at all. It has simply run out of opposition. There is a stillness in this moment that belongs only to scale. Nothing visible on the surface needs to happen yet. The outer layers are too far above the core, too massive, too slow to know immediately what has changed below them. Light cannot carry the message instantly through so much stellar matter. The star may look whole. Its surface may still cast blue-white light into space. To a distant telescope, it may remain a normal supergiant for a little longer. In the center, the old balance is gone. The iron core begins to fall inward. Not the way a stone falls through air, but as matter surrendering to its own gravity from every direction at once. There is no empty space below it. There is no ground. The center falls into itself. Outer parts of the core fall after inner parts. Layers that had been supported by pressure now move inward because the support has been weakened and removed. The collapse begins as a physical consequence, not as an explosion. This matters because a supernova is often imagined as a star simply blowing outward. The first motion is the opposite. The death of the massive star begins with an implosion buried deep inside it. The outer brightness is still a mask. The real event starts in darkness, under layers of plasma and ash, where iron can no longer burn and electrons can no longer hold the weight. For a brief time, the star contains two truths. On the outside, it is still luminous. On the inside, it has already crossed a boundary. The center has stopped being a furnace and has become a falling core. Silicon burning has made the iron. Iron has ended the sequence. Quantum pressure is failing. The next movement will be faster than the star's surface can announce. The star has reached the place where fuel, heat, and patience no longer matter. Gravity has waited through every stage of burning, through every shell of fire, and every layer of ash. It does not need to hurry. Once the iron core can no longer answer, the inward pull begins to write the final physics of the star. The collapse has started. The first motion of a supernova is inward, long before the star brightens in a distant sky, long before its outer layers are thrown into space, long before the gas around it begins to glow with the color of newly heated debris. The center falls. It falls where no eye can reach it, under layers of plasma, ash, and burning shells that still seem to belong to a living star. The surface gives almost nothing away. A massive star in its last moments may still look like a star. Its outer atmosphere can remain bright. Its winds can continue streaming into space. Light can still leave its surface, cross the surrounding darkness, and arrive at distant worlds as if the star were only continuing its ordinary life. The outer layers do not yet know what the core has done. They cannot know instantly. The message has to move through matter, and the matter above the core is deep, heavy, and opaque. Inside, the old support has already failed. The iron core is no longer a place where useful fusion can continue. Silicon burning above it has spent its final gift, adding more iron group material to the center until the core has become too heavy for electron degeneracy pressure to carry with comfort. The electrons are crowded into high-energy states, resisting compression by the rules of quantum physics, but the core is being pressed past the range, where that resistance can keep the star in balance. Photodisintegration begins taking energy from the core. Gamma rays, born in the heat of billions of degrees, strike iron nuclei and break them apart into smaller pieces. This does not release energy, it consumes it. The core pays energy simply to undo the nuclei it once built. Heat that might have helped maintain pressure is spent breaking iron into fragments. It is a quiet theft at the center of the star. Electron capture deepens the loss. Electrons, once part of the pressure that helped hold the core open, are forced into protons. Each meeting makes a neutron and a neutrino. The neutron stays behind. Adding to the changing character of the core, the neutrino leaves if it can, carrying energy away into the overlying star. In ordinary matter, a neutrino would pass through almost anything without a trace. In the early moments of collapse, many of them still escape. They pour out of the core in a ghostly stream, not as light, not as heat that the surface can show, but as particles barely willing to touch the universe at all. The core loses pressure, it loses energy, it loses electrons. Gravity needs nothing more. There is no sudden decision point that the star experiences like a sound or a crack. The collapse follows from the equations of matter under weight. The center begins moving inward, and once the motion begins, it feeds itself. Compression raises density. Higher density increases electron capture. More electron capture removes more pressure. Less pressure allows faster compression. The falling core is not merely dropping, it is being transformed while it falls. Matter that had filled a region roughly comparable to a small planet starts to shrink toward the size of a city. The change happens in a fraction of a second, too fast for the outer star to respond as a whole. The inner core falls almost together, while the surrounding material follows with a delay, each layer drawn inward by the disappearance of support below it. There is no solid surface inside the star, no shell that can catch the collapse and hold it. The center is becoming denser than any ordinary substance can remain. At first, the collapse is almost silent, in the only way a star can be silent. There is no sound traveling out to space. Sound needs matter, and the vacuum around the star carries none. Inside the star, pressure waves and motion exist, but they are buried under so much material that nothing at the surface reveals them immediately. A telescope far away would still record light from the outer layers. That light began its escape before the core completed its fall. It is a late report from a star whose center has already changed. This delay gives the final moments a strange double life. The visible star belongs to the past by a small but important margin. The hidden core belongs to the present. The surface may still glow smoothly, but the center is now collapsing at a speed that makes the older stages of stellar life seem almost still. Hydrogen burning took millions of years. Helium burning took far less. Carbon, neon, oxygen, and silicon burned in shorter and shorter chapters. Now the last chapter is no longer a burning stage at all. It is a fall. As the core contracts, density climbs through levels that have no earthly comparison. Atomic structure has already vanished. Nuclei and electrons no longer behave like familiar atoms. The electrons are being absorbed. Protons are being changed into neutrons. The matter grows more neutron-rich, more compact, more tightly packed. The distance between particles shrinks until the interior begins moving toward nuclear density, the density found inside atomic nuclei themselves. This is an important threshold. Ordinary matter is mostly empty space. Atoms feel solid because of electric forces, but the nucleus at the center of each atom is tiny compared with the space occupied by its electrons. In the collapsing core, that emptiness is being removed. The old architecture of atoms is gone. Matter is being pressed toward a state in which nuclei no longer remain separate in the usual way. The core is becoming something closer to one enormous nuclear body. Before that threshold is reached, the neutrinos change their behavior. In lower density matter, they escape easily. But as the core grows denser, even neutrinos begin to have trouble leaving. The matter becomes so packed that a particle famous for slipping through planets can be scattered and delayed. The core starts to trap its own ghost particles. They no longer stream out freely from the deepest regions. They diffuse outward, slowly compared with the collapse itself, storing part of the energy that will matter later. This trapping does not stop the fall. It only changes what the falling core carries with it. The interior is now a hot, dense mixture of neutrons, protons, electrons, radiation, and trapped neutrinos, squeezed into a smaller and smaller volume. The temperature rises sharply. The pressure changes character. The old support from electron degeneracy has weakened, and a new kind of resistance has not yet fully arrived. The core is between states, crossing a narrow bridge from stellar matter into the matter of neutron stars. Above it, the rest of the star begins to move inward as well. Shells that had been arranged around the iron core lose their foundation. Silicon-rich material falls. Oxygen-rich material follows. The inner layers of the star rain toward the center, not in drops, but as vast regions of plasma drawn inward by gravity. The earlier onion-like structure is still there in composition, but it is no longer a quiet stack of burning shells. It is becoming an inward flow. The outermost envelope remains behind for the moment. It is too distant in stellar terms, too large and slow to take part immediately. This is why the visible star can still appear intact. The collapse is a message that has not yet reached the surface. In the heart of the star, however, the timescale has become shorter than the time it takes ordinary light to cross many familiar distances. The core is contracting, heating, and changing identity while the surface continues to shine. There is a kind of mercy in that delay. The universe does not show the collapse the moment it begins. It lets the old light keep traveling for a little longer. It lets the star appear whole while the deepest part is already gone from its former life. A star can die at the center before it dies to the sky. The collapse continues until matter is squeezed close to nuclear density. At that point, the particles in the inner core can no longer be pressed together in the same way. The strong nuclear force, attractive at one range and fiercely resistant at another, begins to answer compression. The falling matter approaches a wall that is not made of stone, not made of iron, and not made of any familiar solid. It is made of the behavior of nuclear matter itself. The inner core is still falling. The outer core is still falling after it. The shells above are beginning their own descent. The surface still waits in delayed brightness. In less than a breath, the center will stop collapsing not because gravity has weakened, but because matter has reached a density where a new resistance appears. The star has not exploded yet. It has only fallen far enough for the next motion to become possible. The inner core does not continue falling forever. It reaches a density where matter stops behaving like the matter of stars and begins behaving like the matter inside an atomic nucleus. Protons and neutrons are pressed so close together that the old empty spaces of atoms have vanished. The center of the star has become a dense nuclear body, small enough to fit across a city, heavy enough to carry more mass than the sun. At that density, the strong nuclear force changes the movement of the collapse. At certain distances, this force binds nuclear particles together. At still shorter distances, it resists further compression with sudden strength. The inner core, falling inward, at a speed that belongs only to the last fraction of stellar death, meets that resistance almost all at once. Its inward motion stops. Not gently, not with a slow settling. It halts in a moment so brief that the idea of motion itself seems to fold back on the star. The inner core rebounds. This rebound is often imagined as the explosion. It is easy to picture the core striking some invisible floor, bouncing outward, and sending a blast through the star that tears it apart. The image is simple, and for a while it seemed close to the truth. The collapsing center reaches nuclear density. The inner core bounces. A pressure wave races outward through the material that is still falling in. That pressure wave steepens into a shock wave, a moving wall where the conditions on one side are sharply different from the conditions on the other. Behind it, matter has been heated and pushed outward. Ahead of it, matter is still falling toward the center. If the shock wave could travel cleanly through the star, the story would be over quickly. The core would collapse, bounce, and the shock would carry enough energy to blow the outer layers into space. A massive star would die in a single clear motion, inward then outward, but nature does not make it so clean. The shock wave almost dies. This is one of the quiet surprises in the physics of supernovae. The first shock born from the bounce is not usually strong enough to finish the work by itself. It begins with energy, but it is moving through one of the least forgiving places in the universe. Material above the inner core is still falling inward. The shock must slow that material, stop it, heat it, and try to push it back out. Every layer it meets takes energy from it. The wall of outward motion has to fight a rain of matter coming down from above. Then, photodisintegration returns. The shock heats the infalling material to such high temperatures that iron and other heavy nuclei in its path are broken apart. Breaking those nuclei costs energy. The shock pays the cost. Energy that might have driven the blast outward is spent undoing atomic nuclei, splitting them into smaller pieces. The same process that weakened the iron core before collapse now weakens the shock after bounce. The outward motion slows. The shock loses strength. It moves away from the newborn compact center, then stalls at a distance that is small compared with the star, but large compared with the new core. It hangs there, no longer advancing in a clean wave. Below it is the forming proto-neutron star, hot and dense, still settling from collapse. Above it, more material continues to fall inward. The shock has not vanished, but it has stopped being the easy answer. For a time, the supernova seems as if it should fail. This failure was not just a poetic difficulty. It appeared in computer simulations. Early models that treated the star as a perfectly spherical object often found the same problem. The bounce launched a shock, but the shock lost energy and stalled. Without another source of power, the matter above would keep falling. The proto-neutron star would gain more mass. If enough material collected, even neutron matter would not hold, and the center would collapse again, this time into a black hole. The star might disappear with little visible glory, its outer layers never fully thrown into space. Yet supernovae are seen. Their remnants expand across the galaxy. Their light curves rise and fade. Their debris carries oxygen, silicon, calcium, iron, and other elements into the interstellar dark. Something must revive the stalled shock. The answer comes from particles that barely seem able to do anything at all. Neutrinos are born in enormous numbers during the collapse and early cooling of the proto-neutron star. They form when electrons and protons combine into neutrons. They form in the dense, hot matter as the newborn core tries to shed energy. Most particles would be trapped completely in such material. Neutrinos interact so weakly that they can pass through whole planets almost without noticing. But in the region around a newborn neutron star, the densities are so high and the number of neutrinos so vast that a small fraction of them do give up energy to the matter behind the stalled shock. A small fraction is enough. The proto-neutron star releases most of the supernova's energy not as light and not as the motion of the outer gas, but as neutrinos. The visible explosion is only a small part of the total event. The hidden flood of neutrinos carries away the deep energy of the collapsed core. As they stream outward, some are absorbed by neutrons and protons in the hot material below the stalled shock. Each absorption deposits energy. Individually, the events are tiny. Together, across an immense flow of neutrinos, they begin to matter. The material behind the shock warms. Its pressure rises. The stalled shock, which had been held in place by infalling layers and its own energy losses, begins to receive support from below. It does not revive like a switch being turned. It is more gradual. Heat gathers, pressure builds, matter churns. The region behind the shock becomes unstable and alive with motion. This motion matters because a real collapsing star is not a perfect sphere. It may begin nearly round, but the flow inside it develops patterns. Hotter material rises, cooler material sinks. This is convection. The same broad principle seen when heated fluid moves, because warm regions become buoyant. Inside the collapsing star, neutrino-heated matter rises toward the stalled shock, carrying energy upward. Cooler material moves down toward the heating region, where it can absorb more neutrino energy. The flow becomes a slow violence of circulation, not smooth, not even, but useful. Convection helps the shock breathe again. There is also a larger motion known as the standing accretion shock instability, often shortened to SACE. The stalled shock does not remain perfectly round. It can wobble, stretch, and slosh. One side may push farther outward, while another side retreats. The shape shifts. The shock finds uneven paths through the infalling matter. Instead of pushing everywhere with equal difficulty, it may begin to move outward more strongly in some directions than in others. This asymmetry helps the explosion begin. The star does not die like a neat diagram. It dies with turbulence. Behind the shock, neutrino heating, convection, and large-scale sloshing work together. They add pressure. They keep matter in the heating region longer. They let some regions push outward, while others are still receiving infalling gas. The stalled shock begins to move again. At first the motion may be uneven and hesitant. Then it strengthens. The shock starts outward through the shells that once surrounded the iron core. Silicon, rich layers, oxygen, rich layers, carbon and helium, and perhaps far beyond them a vast hydrogen envelope. As it moves, the shock heats the material it crosses to extreme temperatures. Nuclear reactions ignite suddenly in places where the star's ordinary life could no longer sustain steady burning. This is explosive nucleosynthesis. Silicon can be driven toward nickel and iron. Oxygen can be transformed into silicon and sulfur. Other nuclei are rearranged in the brief heat behind the passing shock. The explosion does not merely remove the star's layers, it changes them as it goes. The outer star finally receives the news from its center. The shock reaches wider and wider regions. Layers that had been shining quietly are lifted, heated, and hurled outward. The supernova becomes visible only when this buried motion reaches places where light can escape. The event that began as an inward collapse now becomes an outward release. But the release is not simple. It is the outcome of a near failure. The star does not explode because the first shock was unstoppable. It explodes because the first shock stalls, waits in the hot darkness above the newborn neutron star, and is fed by particles that almost never touch matter. It explodes because symmetry breaks, because heated matter rises, because the shock wobbles and finds a way through. The supernova is born from collapse, rebound, failure, and revival. At its center, a compact remnant remains, flooding its surroundings with neutrinos. Around it, a shock wave begins its long outward passage. Above it, the old shells of the star are about to be torn open. The light has not fully arrived yet, but the hidden engine has awakened. Before a supernova becomes light, it becomes a nearly invisible message. The message leaves the collapsing core as neutrinos, small particles that cross matter with such indifference that most of them pass through planets, stars, and bodies without touching a single atom. They are made in the deepest place of the event, where the core has fallen, bounced, and begun cooling from a temperature so high that ordinary words lose their scale. A supernova can therefore begin with something almost impossible to see. Not a flare, not a brightening in the sky, not a shell of gas rushing outward in color and heat. First, there is a flood of ghostly particles carrying away the energy of the newly formed compact core. Light waits behind layers of stellar material. Neutrinos do not wait in the same way. They begin to leave while the shock is still fighting its path outward. This is why the first true signal of a core collapse can arrive before the visible explosion. The star's outer layers are thick. The shock wave needs time to travel from the buried center to the surface. Until that shock breaks through, the star may not yet brighten dramatically. But neutrinos, born in the core itself, can move outward far more freely. They slip through regions that stop light. They pass through the overlying star like a whisper through walls. The most famous example came from a star that died in the Large Magellanic Cloud, a small companion galaxy of the Milky Way. In February of 1987, a blue supergiant ended its life as the closest observed supernova in centuries. The event became known as SN 1987A. Its light reached Earth after traveling for about 168,000 years. By the time human eyes and telescopes saw the new star brighten in the southern sky, the physical explosion had already taken place long ago in that neighboring galaxy. Yet the most important signal did not arrive first as visible light. Underground detectors on Earth recorded a small handful of neutrinos from the collapse. Only a few dozen particles were captured across multiple instruments. That sounds almost like nothing beside the number released by the supernova itself. The collapsing core emitted a number of neutrinos so vast that it cannot be held easily in imagination. Nearly all of them passed through Earth as if the planet were a faint mist. A tiny number interacted, enough to be noticed, enough to change astrophysics. Those detected particles arrived before the visible brightening was recognized. They confirmed a central idea of core collapse theory. The star's heart dies first. The visible supernova is delayed because the shock must travel outward through the star before light can escape in full. The neutrinos leave from the hidden center, carrying news of the collapse before the surface has finished responding. In that sense, SN 1987A was not only seen, it was felt by instruments waiting in the dark. The detectors were buried underground to shield them from ordinary cosmic ray noise. They were not built as telescopes in the usual sense. They did not form images of the sky. They waited for rare flashes produced when a neutrino happened to interact with matter inside a tank of water or other detector material. Most of the time, nothing happened. Then, within a brief interval, several events appeared close together. Tiny marks from particles that had crossed intergalactic space and entered Earth before the light of the supernova had fully announced itself. There is something gentle about the scale of that evidence. A star larger than the Sun collapsed and released nearly all of its gravitational energy in neutrinos. The event reshaped matter, forged elements, and left behind a growing remnant. And on Earth, the first direct evidence was only a scattering of detections in quiet instruments under rock. The universe had shouted in neutrinos, but matter heard only a few syllables. Those few syllables mattered. They showed that the basic picture was right. A massive star does not explode from its surface inward. The center collapses. A proto-neutron star forms. Neutrinos stream outward in enormous numbers. Only later does the shock reach the outer layers and make the event bright to ordinary telescopes. The light is the part the sky can show. The neutrinos are the part that comes from the engine itself. After SN 1987A, the study of supernovae changed. Astronomers no longer thought of a supernova as only an optical event, a sudden star appearing in a telescope or on a photographic plate. It became a multi-messenger event, something that can speak through light, particles, and, in some cases, ripples in space-time. Each messenger leaves from a different region. Each carries a different part of the story. Light tells of heated gas and radioactive debris. Neutrinos tell of the core. Gravitational waves, if detected from a future nearby collapse, would tell of asymmetry, motion, and the shape of the fall itself. The neutrino signal is especially valuable because it comes from a place that light cannot directly reveal. The core of a collapsing massive star is hidden behind layers of dense material. Photons scatter, absorb, and reappear. They cannot simply report what is happening at the center. Neutrinos can. They are not perfect messengers, because even they become partly trapped in the densest phase and diffuse outward over time, but they still carry information from far deeper than light can reach. In the quiet language of astronomy, this makes them precious. A future supernova in the Milky Way would release a neutrino burst that detectors across Earth could measure in great detail. Thousands, perhaps far more, might be captured depending on the distance and the sensitivity of the instruments. Before the star brightened fully in visible light, alarms would pass through observatories. The neutrino burst would point toward the sky, giving astronomers time to look. Telescopes would turn. Radio dishes would listen. Gravitational wave detectors would search their data. The death of a star would become a coordinated act of listening, but SN 1987 remains special because it gave the first such glimpse. The remnant is still young. Its rings and debris continue expanding. The material shed by the star before the explosion has been struck by the blast and lit in changing patterns. Observatories have watched it for decades, seeing the aftermath unfold slowly compared with the violence that began it. The supernova did not end when the light faded from its peak. It became a laboratory expanding through time. Deep in that remnant, astronomers long searched for the compact object that theory said should remain. If the core collapse left a neutron star, it would be hidden by dust, gas, and glowing debris. For many years, the center did not reveal itself clearly. The neutrino detection had already testified that a compact core formed, but the remnant's heart stayed difficult to see. Then infrared observations from JWST gave strong evidence for emission linked to a neutron star inside the remnant. The center, hidden for decades behind the aftermath of its own birth, began to leave a more direct trace. That long delay gives the story a slow shape. First came the neutrinos, crossing space almost without resistance. Then came the visible light, rising as the shock reached the surface and the debris expanded. Then came decades of watching rings brighten, knots shift, dust glow, and the remnant settle into its young form. Finally, instruments sensitive to infrared light found signs of what may be the compact remnant at the center. A supernova is not a single moment. It is an event with echoes. The ghost signal comes first, but it does not explain everything alone. Neutrinos tell of collapse and cooling. Light tells of expanding material. Infrared observations show dust, hidden structure, and warm debris. X-rays show hot shocked gas. Radio waves show energetic particles and magnetic fields. Each wavelength is a different window into the same death. The star becomes understandable only when those windows are placed together. Still, there is a quiet beauty in the order of arrival. The particles that almost never touch matter are the earliest messengers from the core. They leave before the sky knows what has happened. They cross the space between galaxies. They pass through Earth in uncountable numbers. A few are caught. A few marks in a detector become evidence that, somewhere far away and long ago, the center of a massive star collapsed into a new state of matter. The visible supernova is bright enough to command attention. It can outshine neighboring stars, light surrounding gas, and leave behind a remnant that grows for centuries. But the first announcement is almost invisible, a brief rain of neutrinos, a hidden clock starting before the light. In the death of a massive star, the universe sends its deepest news quietly. When the shock wave begins moving outward through the star, the center does not leave with it. The outer layers are lifted, heated, and thrown into space, but the collapsed core remains behind. It is no longer the iron core that existed before the fall. The old matter has been crushed, changed, and rearranged. Electrons have been forced into protons, neutrinos have poured away. The center has crossed into a state that ordinary stars never reach. What remains depends on mass. If the collapsed core is not too heavy, it settles into a neutron star. This is one of the densest, stable objects known in the universe. It may contain more mass than the Sun, compressed into a sphere only a few dozen kilometers across. The word sphere sounds too simple for it. A neutron star is not a small version of a planet. It is not rock, metal, gas, or plasma in the familiar sense. It is matter pressed toward nuclear density, held up by the behavior of neutrons and by the deeper rules of dense nuclear matter. The surface is thin compared with the whole object, but even that surface is strange. There may be a crust of neutron-rich nuclei arranged under pressure that no laboratory on Earth can fully reproduce. Beneath it, matter becomes denser and more uncertain. Physicists can describe some of its behavior, but the exact interior of a neutron star is still an open question. It may contain superfluid neutrons, superconducting protons, or phases of matter that only exist when pressure has become almost impossible to imagine. The star has died, but the remnant is still a frontier of physics. A newborn neutron star is extremely hot. It cools first by releasing neutrinos, then more slowly by radiating from its surface. For centuries or longer, it can glow in X-rays, a small ember left at the center of a vast expanding cloud. Around it, the debris of the supernova spreads farther each year. Inside it, heat from the collapse is stored in matter so dense that cooling becomes a long, quiet process. The remnant may also spin. The core of the original star had rotation before it collapsed. As the core shrank from a planetary scale to the scale of a city, conservation of angular momentum forced that rotation to speed up. The same principle appears in a skater drawing in the arms during a spin. But inside a star, the effect is carried to a different scale. A neutron star can rotate many times each second. Some rotate hundreds of times each second. The surface near the equator can move at a significant fraction of the speed of light, while the object remains bound together by gravity and nuclear forces. Rotation alone would be strange enough. But neutron stars also inherit and intensify magnetic fields. When the core collapses, magnetic field lines are compressed into a far smaller volume. The field strengthens enormously. In some neutron stars, the magnetic field is already far beyond anything produced on Earth. In magnetars, it becomes stronger still, capable of changing the behavior of matter and light around the star. A magnetar is not larger than an ordinary neutron star in any simple way. It is the field around it that makes it so severe. If a neutron star's magnetic poles are not aligned with its rotation axis, beams of radiation may sweep through space. When one of those beams crosses Earth, radio telescopes detect pulses. This is a pulsar. The pulses can arrive with astonishing regularity, not because the star is sending messages, but because the rotation is precise. A lighthouse does not need intention to sweep light across the sea. A pulsar does not need intention to mark time across the galaxy. The discovery of pulsars revealed that supernova remnants could leave behind active centers. The star that exploded was gone, but not everything had become debris. A compact object remained, spinning, cooling, and shaping its surroundings. In the Crab Nebula, the remnant of a supernova seen nearly 1,000 years ago, a pulsar sits near the center and feeds energy into the surrounding gas. The nebula is not glowing only from the memory of the original blast. It is still being stirred from within. Other remnants hide their centers more carefully. Some neutron stars are faint, some are wrapped in dust and heated gas. Some may not point their beams toward Earth, so they do not appear as pulsars. A neutron star can be present without making itself obvious. The absence of pulses is not the absence of a remnant. It may only mean the beam is aimed elsewhere, or the magnetic field and rotation have settled into a quieter form. If the collapsed core is too heavy, the story changes. Neutron degeneracy pressure, nuclear forces, and the structure of dense matter can only resist gravity up to a limit. The exact limit is still being studied because it depends on the equation of state of matter at densities beyond the atomic nucleus. Observations of heavy neutron stars help narrow the range, but the final boundary is not yet known with perfect certainty. Somewhere beyond roughly 2 to 3 solar masses, a stable neutron star can no longer remain stable. Past that boundary, collapse continues. A black hole forms when the remnant becomes so compact that an event horizon appears around it. The event horizon is not a surface like the crust of a star. It is a boundary in space-time. Once matter or light crosses it inward, no signal can return to the outside universe. The collapsed core has passed beyond visibility. What remains can be known by its gravity, by the motion of nearby matter, by X-rays from gas falling in, or by gravitational waves in mergers. It cannot be seen as a surface. Some black holes may form after a brief neutron star phase. The core first rebounds and creates a proto-neutron star. The explosion begins, but some ejected material does not escape. It falls back. If enough fallback material lands on the neutron star, the mass can push it beyond stability. The neutron star then collapses into a black hole, perhaps seconds or minutes after it was born. A remnant can therefore change identity almost immediately after the supernova begins. In other cases, the explosion may fail more completely. The shock stalls and is never revived with enough strength. Material keeps falling inward. The forming compact object grows heavier until a black hole forms, and the outer layers may be swallowed or only weakly ejected. From far away, such an event might not look like the classic bright supernova at all. A massive star may dim, fade, or seem to vanish. The sky loses a point of light without the expected blaze. These possible failed supernovae are difficult to study because their defining feature is absence. Astronomers must watch many massive stars over time and notice when one disappears. Dust, variability, and hidden companions can complicate the interpretation. A vanished star is a clue, not always a finished verdict. Still, the idea carries weight. Not every massive star may give the galaxy a bright farewell. Some may end by folding into darkness. This does not make the ending less important. A black hole born from a failed or weak supernova still changes its surroundings. If it remains in a binary system, it may later pull gas from a companion star and shine in X-rays. If it merges with another compact object millions or billions of years later, it may release gravitational waves that cross the universe. A quiet collapse can have a long afterlife. Neutron stars have long afterlives too. In pairs, they can spiral together as gravitational waves carry orbital energy away. When two neutron stars finally merge, they produce some of the heaviest elements in the periodic table through rapid neutron capture. Gold, platinum, and other rare nuclei can be born in that final collision. A remnant of one supernova may therefore wait for another compact remnant, circling through deep time before giving the universe a second kind of creation. At the center of a supernova, then, the ending is not one ending. It is a fork. One path leaves a neutron star, hot and dense, sometimes pulsing like a clock, sometimes wrapped in magnetic fields strong enough to reshape nearby space. Another path leaves a black hole, quiet at the boundary, known by what moves around it and by what can never return. A third path may barely show an explosion at all, leaving behind darkness where a giant star once shone. The outer debris keeps expanding around whichever center survives. Gas races outward. Heavy elements spread. Dust begins to form. Light fades from its peak. The remnant grows wider, thinner, and more transparent with time. At the middle, something compact remains or has vanished behind an event horizon. The star is gone as a star. But its center has become one of the universe's most concentrated forms of memory. Not every supernova begins with the collapse of a giant star. Some begin much later, after a star has already died once. The first death may have been quiet, almost gentle by comparison. A sun-like star swelling into a red giant, shedding its outer atmosphere into space and leaving behind its exposed core. That core becomes a white dwarf, small, dense, hot at first, and then slowly cooling through ages of darkness. A white dwarf is a stellar remnant, but it is not a neutron star. It is not made of matter, crushed to nuclear density. It is usually a ball of carbon and oxygen about the size of Earth, with a mass that can be comparable to the Sun. No fusion burns steadily inside it. The star's active life is over. What remains is supported by electron degeneracy pressure, the same quantum resistance that once tried to hold up the iron core of a massive star before collapse. Left alone, a white dwarf would not explode. It would fade. It would radiate away its stored heat, growing dimmer over billions and then trillions of years. The universe is not yet old enough for any white dwarf to have cooled completely into a black dwarf. Even the oldest of them still carry some leftover warmth from the stars they used to be. Alone in space, they are patient remnants. But many stars are not alone. In a binary system, a white dwarf may orbit another star. That companion might be a normal star, still burning hydrogen. Or it might swell into a red giant as it ages. If the companion's outer layers expand far enough, material can begin flowing toward the white dwarf. Gravity draws the gas across the space between them. Because the gas carries orbital motion, it does not fall straight down. It forms a disk, a flattened whirlpool of hot material, circling the white dwarf before settling onto its surface. This is accretion. It is slow compared with an explosion, but it changes the future of the dead star. Layer by layer, the white dwarf gains mass. Its gravity strengthens. Its interior is compressed. Density and temperature rise, especially near the center. The white dwarf is still supported by electron degeneracy pressure, but the support has a known limit. As the mass approaches the Chandrasekhar limit, near 1.4 times the mass of the Sun, the remnant moves closer to a threshold it cannot cross gently. The material inside the white dwarf is not iron, it is mainly carbon and oxygen, and those nuclei can still fuse if conditions become severe enough. In an ordinary living star, fusion is regulated by expansion and cooling. If a core heats too much, pressure increases, the gas expands, the temperature drops, and the reaction slows. The star has a kind of thermostat built into its structure. A white dwarf has no such ordinary thermostat. Its pressure does not depend mainly on temperature. It depends on density and quantum rules. When carbon fusion begins under degenerate conditions, the heat does not cause the star to expand enough to slow the reaction. The temperature rises, the fusion rate rises with it. More fusion releases more heat, and the hotter matter fuses faster still. A closed loop forms, and it runs away. The result is a thermonuclear supernova. This is the event called a Type 1 supernova. It does not come from an iron core losing its fight with gravity. It does not require a massive star still alive in its final burning shells. It does not begin with core bounce or a stalled shock revived by neutrinos. It begins when a dead carbon-oxygen remnant is pushed into runaway fusion. The fire spreads through the white dwarf, converting carbon and oxygen into heavier elements, especially nickel and iron group material. In only a few seconds, the entire star can be destroyed. There is no neutron star left behind. There is no black hole at the center. In the classical picture, the white dwarf is unbound completely, its matter thrown outward into space. The remnant that remains is not a compact object, but an expanding cloud of debris, rich in iron group elements and glowing because radioactive nuclei made in the explosion are decaying into more stable forms. The death is total in a way core collapse is not. A massive star loses its outer layers, but leaves a central object. A Type Y, a white dwarf, gives up the whole of itself. This path is called the single degenerate scenario. One degenerate star, the white dwarf, and one non-degenerate companion feeding it material. For many years, it was the standard picture. It is still an important path. Some systems show white dwarfs accreting from companions, and some may be moving toward conditions that resemble the beginning of such an event. Yet the universe often offers more than one route to the same light. Another path begins with two white dwarfs orbiting each other. Both are stellar remnants. Both have already passed through their quiet first deaths. As they orbit, they emit gravitational waves, faint ripples in space-time that carry energy away from the binary system. The orbit shrinks slowly. The stars spiral closer over millions or billions of years. At the end, they merge. The merger is not calm. The less massive white dwarf may be torn apart by tidal forces and spread into a hot stream or disk around the other. The combined system can become unstable. Compression, heating, and rapid mixing can ignite carbon fusion. If the conditions are right, the result is again a thermonuclear destruction of the white dwarf material. No living giant star is needed. Two dead stars can create one of the brightest explosions in the universe. This is the double degenerate scenario. It matters because astronomers do not always find surviving companion stars near Type Y, remnants. If a normal companion had fed the white dwarf and survived the explosion, there might be a scarred star left behind, moving through the remnant with unusual speed or composition. In some cases, no such companion appears. That absence suggests that at least some Type Y, a supernovae, come from mergers of two white dwarfs, where no ordinary star remains to be found. There are still other variations. In some models, a white dwarf does not need to reach the Chandrasekhar limit exactly. A layer of helium on the surface may detonate first. That surface detonation can send a shock inward, compressing the carbon-oxygen core and triggering a second detonation. This double detonation path can destroy a white dwarf below 1.4 solar masses. It helps explain why Type Y, a supernovae, are similar enough to be useful, yet not identical in every detail. The similarities are important. Type I, a supernovae, tend to produce large amounts of radioactive nickel. As nickel decays into cobalt and then iron, it heats the expanding debris and powers the visible light for weeks. Because the explosions often involve white dwarfs in related physical conditions, their peak brightnesses fall into a range that astronomers can calibrate. They are not perfectly identical candles, but their light curves carry a pattern. Brighter ones fade more slowly, dimmer ones fade more quickly. That relationship makes them measurable across enormous distances. Before that larger cosmic use, though, they remain stellar endings. A Type Y, a supernova, is the second death of a star that once avoided the violence of core collapse. The original star may have lived a long life, exhausted its central fuel, cast off its outer layers, and settled as a white dwarf. For ages, it may have seemed finished. Then gravity from a companion, or a slow spiral with another remnant, returned it to crisis. The dead star was not revived into life. It was pushed into one final act of fusion that could not stop itself. This kind of ending is quieter in its beginning and more complete in its result. There is no giant envelope to tear through. There is no newborn neutron star cooling in neutrinos. There is no pulsar at the center to keep time after the blast. There is only the white dwarf, compressed past safety, burning through itself until nothing compact remains. Both kinds of supernova carry matter back into the galaxy. Both can outshine their host stars for a time. Both seed space with heavy elements, but their inner meanings are different. One is the failure of a massive living core. The other is the runaway burning of a compact stellar corpse. One begins with gravity winning. The other begins with fusion escaping control. The sky gives them the same old name, supernova. Beneath that name are two very different ways for a star to end. A Type 1, a supernova, begins as the destruction of a white dwarf, but its light does not remain only a local event. It travels beyond the torn debris, beyond the galaxy that held the dead star, and across distances so large that the explosion becomes something else to astronomers. It becomes a measure. The white dwarf is gone. Its carbon and oxygen have burned through runaway fusion. Nickel and other iron group elements have been thrown outward in an expanding cloud. As that radioactive nickel decays into cobalt, and cobalt later decays into iron, the debris remains warm and luminous. The light rises, peaks, and then fades in a pattern that can be recorded with careful observations. The shape of that fading is the important part. It is not random. It carries information. For a long time, astronomy has depended on objects whose true brightness can be understood. If the true brightness of an object is known, and the object appears faint, then the distance can be found. A lamp across a field looks dimmer than the same lamp nearby. The light has spread out. The farther it travels, the thinner it becomes. The same simple fact holds across the universe, though the distances are no longer fields or cities, but galaxies and deep time. Type I, as supernovae, are not perfectly identical. No natural object is. Some are brighter, some are dimmer, some fade a little more slowly, others more quickly. But they obey a useful pattern. The brighter explosions tend to fade more slowly. The dimmer ones fade faster. This relation allows astronomers to standardize them, to correct for their differences, and estimate how bright each one truly was. They are often called standard candles, though standardizable candles is closer to the truth. The phrase sounds small beside the event. A candle is held in a hand. A Type 1, a supernova, is a dead star destroyed by runaway nuclear fire, yet the name works because both are used in the same basic way. The known light of a candle tells distance in darkness. The calibrated light of a supernova tells distance across the expanding universe. This is why the total destruction of a white dwarf became one of the great measuring tools of cosmology. Type I, a supernovae, are bright enough to be seen in galaxies billions of light years away. They appear, rise, fade, and vanish. But during that brief window, they give astronomers a point of reference in a galaxy far beyond reach. Their light curves can be compared. Their spectra can be measured. Their host galaxies can be studied for redshift, the stretching of light that occurs as space itself expands between source and observer. Distance and redshift together tell a deeper story. Redshift reveals how much the universe has stretched since the light began its journey. Distance tells how far away the source was when the light was emitted, after the history of expansion is taken into account. By placing many supernovae at many distances, astronomers can trace how the expansion of the universe has changed over time. For much of the 20th century, the expectation was clear. The universe began expanding after the hot early state commonly called the Big Bang. Matter fills the universe. Matter has gravity. Gravity attracts. Therefore, the expansion should slow down. The question was not whether the expansion was decelerating, but by how much. Would gravity eventually stop the expansion and pull everything back inward? Or would the universe expand forever, slowing more and more, never quite stopping? The answer came from distant Type I, a supernovae. And it was not the expected one. In the late 1990s, two teams measured the light from far away, Type I, a supernovae, and compared their calibrated brightness with the redshifts of their host galaxies. Those supernovae appeared dimmer than they would have appeared in a universe whose expansion was only slowing under gravity. Dimmer meant farther away. Farther away meant that the expansion had not merely coasted outward and slowed, it had changed in a different direction. The expansion was accelerating. This result altered the map of modern cosmology. Something was causing space to expand faster over time on the largest scales. The name given to this unknown cause is dark energy. The name describes what it does more than what it is. It is dark because it does not shine or absorb light in the ordinary way. It is energy because it acts as part of the universe's total energy content. It appears to push the expansion of space rather than pull matter together. The nature of dark energy remains unknown. It may be the cosmological constant, a steady energy of empty space itself. It may be a field that changes slowly over cosmic time. It may point toward a deeper correction in the way gravity is understood on the largest scales. Observations continue to narrow the possibilities, but the central mystery remains open. The universe is expanding faster with time, and the reason is still not fully known. There is a strange softness in the path that led to this discovery. It did not come from touching the edge of the universe. It did not come from traveling outward. It came from watching dead stars flare and fade in distant galaxies, then comparing their light with the stretching of space. White dwarfs, small remnants no larger than Earth, became markers for the behavior of the cosmos as a whole. Their deaths revealed that the largest structure anyone can measure is not standing still, not slowing in the expected way, but opening faster. Each distant Type I, a supernova, is therefore both an ending and a ruler. It marks the death of a compact star system, but it also marks a point in the history of expansion. Its light may have left when the universe was younger, when galaxies were closer together, when the future acceleration had not yet carried them so far apart. By the time that light arrives, the universe has changed. The galaxy that hosted the explosion is farther away than it was when the photons began traveling. Space has grown during the journey. This makes looking outward the same as looking backward. A nearby Type I, a supernova, shows the expansion of the relatively recent universe. A very distant one shows the universe as it was billions of years ago. Placed together, they become a sequence of candles set along time itself. Not candles in a hallway, but brief stellar fires suspended across cosmic history, each one fading after a few weeks, each one leaving a measurement behind. the measurements still require care. Dust in a host galaxy can dim light and make a supernova appear farther away than it is. Different stellar environments can affect the details of the explosion. The white dwarf's composition, the path to ignition, and the amount of nickel made in the blast can vary. Astronomers correct for these effects as carefully as possible, comparing colors, spectra, light curve shapes, and host galaxy properties. The work is patient. The conclusion rests not on one supernova, but on many. Other measurements now support the same broad picture. The cosmic microwave background, galaxy clustering, baryon acoustic oscillations, and large surveys of structure all point toward a universe in which dark energy dominates the present expansion. Type I supernovae were not the final word, but they opened the door. Their fading light showed that something was missing from the older picture. The discovery also changes the far future. If dark energy behaves like a cosmological constant, distant galaxies will recede faster and faster. Over immense time, many will pass beyond the observable horizon. Their light emitted after that crossing will never reach this region of space. Future observers, if any exist in a far future galaxy, may see a much emptier sky. The wider universe will still exist, but much of it will be carried beyond contact by expansion. A white dwarf's final light thus points in two directions. It points backward to the life of a star that once fused hydrogen, swelled, shed its atmosphere, and left a compact core. It points outward to a companion, an accretion disk, a merger, or a surface detonation. It points forward into radioactive fading, iron-rich debris, and the chemical enrichment of space. And it points across the whole universe toward the acceleration that shapes the fate of galaxies. The candle burns only briefly. The darkness it measures keeps expanding. A Type I supernova is gone within weeks as a bright object. But the information in its light remains. It tells how far the host galaxy was. It tells how fast that galaxy's light has been stretched. It joins a quiet collection of other measurements, each one a small mark in the long record of cosmic expansion. From these marks, astronomers learned that the universe is not simply coasting outward after its beginning. It is being carried into a larger, colder separation by something still unnamed in any final sense. The death of a white dwarf became a way to read the future of space. After the first brightness fades, a supernova becomes quieter without becoming simple. The expanding debris keeps moving outward, year after year, into the thin gas between stars. What was once the layered body of a massive star becomes a widening shell of oxygen, silicon, sulfur, calcium, iron, carbon, and dust. The explosion has ended as a flash, but its material has only begun a much slower journey. A supernova remnant is the afterlife of the blast. It is not only a cloud, it is a moving boundary where fast stellar debris meets the older gas around it. The ejected material races outward until it collides with circumstellar and interstellar matter, shocking it, heating it, compressing it, and making it glow in different kinds of light. Some regions shine in X-rays because the gas is extremely hot. Some reveal themselves in radio waves, where energetic particles spiral through magnetic fields. Some appear in infrared light, where dust grains warmed by the remnant give off their hidden heat. Infrared light is especially important because dust often keeps its secrets from ordinary vision. Small grains can absorb visible and ultraviolet light, then re-radiate that energy at longer wavelengths. To eyes, a dusty region can look dark or dim. To an infrared telescope, it can begin to speak. Warm dust becomes visible. Cooler debris can be traced. Knots and filaments that would otherwise blend into shadow appear as structure. Cassiopeia A is one of the clearest places to see this slow aftermath. It is a young supernova remnant in the Milky Way. the remains of a massive star whose light from the explosion reached Earth only a few centuries ago. The original star is gone. In its place is a roughly circular field of debris, expanding into space and still carrying the marks of the explosion that made it. In optical images, X-ray images, radio maps, and infrared observations, Cassiopeia A looks different each time because each kind of light comes from a different part of the remnant's physics. JWST has shown Cassiopeia A in infrared detail that feels almost too fine for an object born from violence. The remnant contains filaments, knots, sheets, and arcs of gas and dust. Some parts are ejecta from the star itself. Some belong to material shed by the star before it exploded. Some are interstellar dust touched by the light of the supernova long after the first blast. The whole structure is not a smooth bubble. It is ragged, mixed, torn, and still moving. This unevenness matters. A supernova is sometimes drawn as a sphere expanding equally in every direction, but real explosions are shaped by turbulence, rotation, magnetic fields, and the uneven layers of the dying star. Material from deep inside can be thrown outward in clumps. Outer material can be pierced by faster knots from below. Heavy elements are not laid down in clean circles. They are scattered in plumes, jets, patches, and shells. Cassiopeia A preserves some of that disorder, like a frozen record of a star that did not die symmetrically. The dust inside such a remnant has a delicate fate. Dust grains can form in the cooling debris after the explosion, as atoms bind into small solid particles. Carbon-rich regions may make carbon dust. Oxygen-rich regions may help build silicate grains. Other elements join into minerals too small to see individually, smaller than smoke, but large enough to change the way light moves through space. In the years after a supernova, the debris cools, chemistry begins, and some atoms that were once plasma become part of tiny grains drifting through the remnant. But the same remnant that makes dust can also destroy it. Shock waves move through the debris and surrounding gas, heating and grinding grains down. Fast particles can chip atoms from their surfaces in a process called sputtering. Collisions can shatter larger grains into smaller fragments. The dust born in the cooling ejecta must survive a difficult passage through waves of heat and impact before it can join the wider interstellar medium. This is why the question is not only how much dust a supernova makes, it is how much dust escapes. Some of the dust may be destroyed before it leaves the remnant. Some may survive inside dense clumps, shielded for a time from the strongest shocks. Some may be carried outward, mixed with gas, and spread into the galaxy. The answer depends on the structure of the explosion, the density of the surrounding medium, the composition of the grains, and the long history of shocks passing through the remnant. A supernova remnant is not one event but a changing environment, and dust must live through that change. The surviving grains are small, but their role is large. Dust helps cool gas clouds by allowing them to radiate energy. It provides surfaces where molecules can form. It absorbs starlight and changes the colors of distant stars. It becomes part of the raw material from which planets grow. In protoplanetary disks around young stars, dust grains collide, stick, break, and stick again, slowly forming larger particles, pebbles, rocks, and eventually planetesimals. A grain that survives a supernova remnant can, in some later cloud, become part of a world. The path is long. Dust from an exploded star does not move straight into a planet. It drifts. It mixes with older gas, older dust, material from red giants, winds from massive stars, and the quiet remnants of many previous stellar deaths. It becomes diluted into the interstellar medium, where atoms and grains from many sources lose their separate histories. Later, a cold molecular cloud, may gather some of that mixed material. Gravity may pull parts of the cloud inward. A new star may form at the center, surrounded by a disk. Inside that disk, dust begins another kind of assembly. The grain no longer carries a label. No planet can look at one speck and know the name of the star that made it. But the chemistry remembers in a statistical way. The presence of silicon, oxygen, magnesium, iron, calcium, and carbon in rocky material reflects the work of earlier stars. Supernovae are part of that inheritance. Their debris does not remain as debris forever. It enters the general reservoir from which later systems are built. This makes a supernova remnant less like a grave and more like a slow mixing bowl of the galaxy. The first light fades. The shock expands. The knots cool. The dust glows in infrared and then dims. Over thousands of years, the remnant grows wider and thinner. Over longer times, it loses its sharp edges and becomes part of the background gas between stars. What began as a named object in a telescope becomes material without a visible boundary. Cassiopeia A is still young enough to keep its shape. Its shell can be mapped. Its knots can be followed. Its light echoes can show where the ancient flash has struck dust at a distance and scattered toward Earth after a delay. Those echoes are reminders that even light from the explosion can have an afterlife. It travels outward, meets dust far from the remnant, reflects, and arrives later, as if the supernova were whispering from another direction after the main voice has faded. There is a soft lesson in that. The explosion is brief, but the aftermath is extended through matter and time. The bright peak lasts weeks or months. The remnant lasts thousands of years. The dust may travel for millions. The atoms may wait through the birth and death of more stars before finding a new place in a planet. The violent event becomes slow material. In the darkness between stars, this slow material matters more than the flash. The flash announces the death. The dust carries the result. It holds part of the star's carbon and oxygen, part of its silicon and iron, part of the ash made before and during the blast. It moves outward into space, sometimes heated, sometimes hidden, sometimes visible only in infrared light. Long after the supernova is no longer bright enough for ordinary eyes, the remnant continues its patient work. Gas expands, shocks fade, grains survive or break, elements mix. The galaxy receives what the star has given back, and somewhere in that mixture, the first quiet ingredients of future worlds begin to drift. The debris of a supernova does not remain only debris. It widens, cools, thins, and begins to lose the sharp outline of the event that made it. The bright remnant becomes part of a larger darkness. Its atoms drift into the interstellar medium where gas from many stars has already mixed for millions of years. Nothing in that medium is pure. It is a long memory of older suns, red giant winds, stellar nurseries, dying massive stars, white dwarf detonations, and compact remnants colliding after ages of silent orbit. This is where the story of a supernova becomes larger than the death of one star. It becomes the story of matter, learning new forms. At the beginning of the universe, there were almost no heavy elements. In the first minutes after the hot early state, the cosmos made mostly hydrogen and helium, with only traces of lithium. There was no oxygen for water, no carbon for organic chemistry, no silicon for rock, no calcium for bone, no iron for blood or planetary cores. The early universe was hot, bright, and expanding but chemically simple. Its future complexity had not yet been forged. Stars changed that. Gravity gathered hydrogen and helium into clouds, then into the first generations of stars. In their cores, hydrogen fused into helium. Later, in suitable stars, helium fused into carbon and oxygen. In massive stars, Later stages made neon, magnesium, silicon, sulfur, calcium, nickel, and iron group elements. The star became a factory of heavier matter, but making the elements was only half of the story. The elements had to be released. A star can hold its ashes for a long time. Carbon and oxygen can remain buried in a white dwarf. Iron can remain locked in a collapsed core. Heavy elements can sit inside stellar interiors where no planet can use them. A supernova opens the locked chamber. It tears material from the star and throws it into space. It takes what was hidden in the center and gives it back to the galaxy. Core collapse supernovae release the layered products of massive stars. Their shocks heat material and drive explosive nucleosynthesis, making new isotopes in the brief furnace of the blast. Type I, a supernovae. The thermonuclear destruction of white dwarfs are especially important for iron group elements. In them, a compact carbon-oxygen remnant burns through itself and scatters large amounts of nickel that later decays into iron. Much of the iron spread through galaxies owes its existence to such white dwarf deaths. The iron in rocky planets, in meteorites, in the deep metallic centers of worlds, and in the chemistry of living blood is part of that old record. It does not come from one star alone. It comes from many stellar deaths, mixed together until no single atom can be traced to a named explosion. Still, the process is real. Iron did not begin on planets. Planets inherited it. Calcium carries a similar history. So does silicon. So does sulfur. The crust of a rocky world is not merely local stone. It is cooled, stellar ash, rearranged by planetary heat, oceans, impacts, plate motion, and time. The minerals in mountains have a past older than the planet that holds them. The atoms were made elsewhere, under pressures and temperatures the planet itself could never produce. Carbon and oxygen have older stellar origins as well. They are made in the interiors of stars before being released by winds, planetary nebulae, and supernovae. They become part of molecular clouds. In cold, dark regions, oxygen binds into water ice on dust grains. Carbon enters simple molecules, then more complex ones. These materials do not make life by themselves, but they provide the alphabet from which later chemistry can write. Elements heavier than iron require another kind of path. Fusion beyond iron does not release energy in the usual stellar way. To build many of the heaviest nuclei, the universe uses neutron capture. In the slow process, or S process, nuclei capture neutrons over long periods in evolved stars and then decay step by step into heavier elements. In the rapid process, or R process, nuclei capture neutrons so quickly that they are driven far from stability before decaying back toward lasting forms. For a long time, core collapse supernovae were thought to be one of the main homes of the R process. They may still contribute in some environments, but the clearest confirmed site is the merger of neutron stars. When two neutron stars spiral together and collide, neutron-rich matter is flung outward, and the conditions become ideal for making heavy elements such as gold, platinum, and uranium. The gravitational wave event known as GW170817 gave direct evidence of this process when a neutron-star merger was detected both in gravitational waves and in light. The glow of that event carried the color and fading expected from newly made heavy elements. This does not remove supernovae from the story. It deepens the story. A neutron star itself is usually born in a supernova. The merger may happen much later, after two compact remnants have orbited each other for millions or billions of years. One stellar death leads to a compact object. Two compact objects may later meet. Their final collision adds another set of elements to the galaxy. Creation is not a single event. It is a chain. The periodic table is therefore a map of cosmic history. Hydrogen points back to the early universe. Carbon and oxygen point to stellar interiors. Silicon, sulfur, calcium, nickel, and iron point to massive stars and supernovae, including the thermonuclear deaths of white dwarfs. Gold and platinum point strongly toward neutron star mergers, with possible help from other neutron-rich explosions. Each element has a birthplace, or more often a family of birthplaces. Matter remembers those places in its abundance. A planet forms from that memory. A cold molecular cloud begins to collapse under gravity. It contains hydrogen and helium, but also dust and heavy elements from earlier generations of stars. At the center, a new star ignites. Around it, a disk of gas and dust flattens and rotates. Dust grains collide. Some stick, some break. Some grow into pebbles, then stones, then larger bodies. Metals sink. Silicates form crusts. Ices collect where it is cold enough. The scattered ashes of older stars become the architecture of a new system. Earth formed this way. It is not made from the first material of the universe alone. It is made from enriched material, from gas and dust that had already passed through earlier stars. The sun formed from the same cloud. The planets formed from what remained around it, the iron that sank into Earth's core, the silicon and oxygen that built its rocks, the carbon that entered its surface chemistry, the calcium that later became part of shells and bones, all came from matter processed before the solar system existed. A human body is one small arrangement of that ancient matter. Oxygen makes up much of its mass, held in water and organic molecules. Carbon forms the framework of life's chemistry. Hydrogen is older still, a survivor from the early universe. Nitrogen, phosphorus, sulfur, calcium, iron, zinc, copper, selenium, and other elements appear in smaller amounts, but each is necessary in its own way. None of them were invented by life. Life borrowed them. This connection is often described as stardust, and the word is gentle enough to remain true. It is not only poetry. The atoms in living tissue have passed through cosmic processes that happened long before the first cell on Earth. Some were inside stars. Some were made in explosions. Some traveled as dust through interstellar darkness. Some entered the cloud that formed the sun, then the disk that formed the planets, then the chemistry of a young world with oceans and rock and atmosphere. The path from supernova debris to life is not direct or guaranteed. Most enriched gas does not become a living planet. Most atoms drift without ever entering biology. The universe wastes nothing in a human sense because it has no need to spend carefully. It mixes, collapses, heats, cools, scatters, and gathers again. Out of that long circulation, certain places become stable enough for complex chemistry. Some of those places become worlds. On at least one world, the ashes of stars learn to move, breathe, and think. This is the final meaning of a supernova, in the calmest sense. It is not only a burst of light. It is not only a collapse, a shock, a neutrino storm, or an expanding shell. It is a transfer. A star returns its inner work to space. The galaxy receives it slowly. Clouds inherit it. New stars and planets form from it. Matter takes another shape. The massive star that died is gone. The white dwarf that detonated is gone. The light fades. The remnant thins. The dust drifts beyond the named edge of the explosion, but the elements remain. And over deep time, they find their way into stones, oceans, atmospheres, cells, and blood. The star does not survive as a star. It survives as everything that comes after. The journey leaves the bright places now. The shock waves have passed into distance. The remnants widen in silence. Dust moves through the dark between stars, no longer carrying the shape of the explosion, only the quiet memory of what the star returned. Far behind, a massive core has fallen into a neutron star or disappeared behind the boundary of a black hole. Somewhere else, a white dwarf has given itself completely to light, leaving no center behind. Their brightness fades from the sky, but their matter continues onward. It drifts into clouds too cold and dim for ordinary eyes, where atoms wait without hurry. There is no need to follow each one further. The universe will do that slowly. It will mix the ash with older gas. It will fold dust into future clouds. It will gather some of that material into stars not yet born, into planets not yet shaped, into oceans and stone, and perhaps, after a span no clock can hold easily, into living things that feel warmth beneath another sun. For now, only the stillness remains. A field of stars, a faint nebula thinning into darkness, a small grain of dust turning without sound, the light of old explosions traveling past worlds that will never know its source. The body can rest in that quiet scale. Breath can slow. The room can become softer around the edges. Outside the window, or beyond the clouds, the sky carries on with its distant work, burning, collapsing, scattering, and beginning again. Nothing needs to be held now. The star has given back what it carried. The galaxy has received it. The darkness is not empty. It is full of things on their way to becoming something else.